All right, this problem is another gas stoichiometry problem, and it comes from the practice test. It is number 8 from the practice test, and it is examining this equation. So dinitrogen pentoxide decomposing into elemental oxygen and nitrogen dioxide. So it's one gas decomposing into two gases. Now to balance this, I am going to need to put, all right, now no matter what I do, I'm only going to get even oxygens on the product side, and I have an odd number of oxygens on the reactant side. So I am going to put a 2 on front of that to fix the odd even issue. Then that means I'm going to need 4. So 2 sets of 2 nitrogen, and this guy only has 1 nitrogen in it, so I'm going to need 4 of those to balance that out. And then that gives me, let's see, this side, 2 sets of 5, so that's 10 oxygens. 4 sets of 2, that's 8, 9, 10. So the 2, the 1, and the 4, that is now balanced. All right, and then the question is, all right, if you have 22 liters of N2O5, so I've got 22 liters of this guy at a pressure of, so pressure is 1.25 atmospheres and temperature is 23 degrees Celsius. What volume of NO2 can be obtained at, so we are looking for volume of NO2 can be produced at temperature of 23.0 degrees Celsius and a pressure of 1.25 atmospheres. Now there are 2 ways that you can work this out. Any stoichiometry problem, always same process, right? You are going to go from the info about the N2O5, and you are going to convert that to moles of N2O5. And then you're going to go from moles of N2O5. You know that for every 2 moles of N2O5, you are going to need 4 moles, or going to produce 4 moles of NO2. So then we can find moles of NO2, and then I want to find liters of NO2. So then I can take moles and go to volume in liters if I have the pressure and the temperature, which I do. So pretty typical stoichiometry problem, and that's how you're going to approach it. So first we need to find moles of N2O5, so we can then find moles of NO2, and then we can ultimately find liters of NO2. If I know volume, pressure, temperature, and what moles, it's going to be ideal gas law, PV equals nRT. And rearrange that to solve for moles. N is going to equal PV over RT. Remember, R is 0.0821 liter atmospheres per mole Kelvin. So liter atmospheres, but temperature needs to be in Kelvin, so we're going to add 273, so that gives you 296 Kelvin. So then that means 1.25 atmospheres times 22 liters divided by 0.0821 times 296 Kelvin, and moles is going to come out to be 1.25 times 1.13 moles of N2O5. And then when I want to convert that, it is 4 moles of NO2 for every 2 moles of N2O5. So that means I can make So times 2, it's going to be 2.26 moles of NO2. And now I want to find volume in liters. And so I know moles, I know pressure, I know temperature. I want to solve for volume. So again, I'm going to use the ideal gas law. And PV equals nRT. I'm going to rearrange to solve for volume. So if PV equals nRT, then volume is going to equal nRT over P. So then we'll plug in those numbers. So we'll do it down here. So volume is going to equal 2.26 moles times 0.0821 times 296 divided by 1.25 atmospheres. 2.26 times 0.0821. And it comes out to be 43.9, and I'm going to say rounded to 2 sig figs, which was that what the original problem had in it? Yeah, only 2 sig figs. So it's going to be 44 liters of NO2. Now, here's the thing that could make this a whole lot easier. We are looking at one gas compared to another gas, and the conditions, pressure and temperature, are the same. And so there is a, let's call it a shortcut to this. All right, so Avogadro's law states that volume is proportional to moles at the same temperature and pressure. And so since pressure is the same, temperature is the same, and we're comparing these two gases, we actually don't need to go through all of this complicated sequence of events. So anytime that's true, you're comparing two gases and it's the same pressure, same temperature, there is a shortcut that you can use. Also notice mathematically, we divided by 296, we multiplied by 296. We multiplied by 1.25, we divided by 1.25. We divided by 0.0821, we multiplied by 0.0821. So mathematically, all of this canceled out, and all we did was take volume of N2O5 times the mole ratio and got the volume of NO2. So when you're looking at gases, they're at the same pressure and temperature, you can read this balanced equation rather than 2 moles of N2O5, 1 mole of O2, 4 moles of NO2. You can read it as 2 liters of N2O5, 1 liter of oxygen, 4 liters of NO2. And if we use this shortcut method, I'm going to go 22 liters of N2O5 times, and it is 4 liters of NO2 for every 2 liters of N2O5 equals liters of N2O5 divide away, and lo and behold, I get 44 liters of NO2, and those answers are the same. But keep in mind that special condition only works comparing gases that are at the same conditions. So your ideal gas law will never steer you wrong, but the shortcut has special circumstances. So there is our last stoichiometry problem that I am going to work out as an example.